Okay, these are the diagrams for the refraction packet in the lesson about lenses. So the first thing we do, just like with mirrors, is to draw a line that's parallel to the axis, and it's going to go to the middle line on the lens. Now remember, this is just an approximation. Actually, it bends when it enters the lens and when it exits the lens, but we can approximate it by just having it bend when it's at the middle of the lens. Okay, that ray refracts to go through the focal point. Once you draw this refracted ray, scribble out the incident ray. You don't need it anymore. It just confuses people. And then we're going to draw the ray that goes through the focal point from the top of the object. And that's going to refract parallel. Once you draw that refracted ray, scribble out the incident ray. So now you ask yourself, where do these two rays appear to have come from? Looks like they came from right there. And so that is the image of the tip of the arrow. And remember that the base of the arrow is always on the axis itself. So the base is above the tip. It must be an upside down image. We can also see that it's reduced. The light rays really do travel through that spot, and so it's a real image. We could put a movie screen there and we'd see it on the screen. Okay, in the second one, we have the exact same object, same height, but it's a little bit closer to the lens. Let's see how that's going to change things. Now imagine in this top image, how is it going to change if the object is closer to the lens? Will this top line change at all? Will its refraction change at all if it's moved up? And now think about the second ray. If this object was closer up, would this ray be any differently drawn? Would it hit the lens in a different position at all? How would it change this parallel line here? We should see that as this object gets closer, this line here is going to get steeper. So it's going to hit the lens at a lower place. So this horizontal line here is going to be in a lower position, which means that the crisscross is going to be lower down, and it's going to be a bigger image. The first line stays exactly the same. It's the same height object, so the parallel line stays the same height over the axis. It's going to hit the lens in the same position. It's going to angle down through the focal point in the same angle. Once I draw that refracted ray, scribble out the ray of incidence. Okay, now here's the line that's going to be a little bit steeper than before. And then it's going to go horizontal, parallel to the axis. It's not a dramatic change, but it is noticeably bigger here than it was up here. So here is our image right there. Third one, a little bit more dramatic in this case. Parallel ray is going to be the exact same as before. Once I draw the refracted ray, scribble out the ray of incidence. This one is going to be very steep. So the image is over here, very large. Now notice that not only does the image get bigger, but it moves away from the lens. Here it's pretty close to the focal point. Here it's a little bit farther away. And here we can tell significantly farther from the focal point. Okay, the next page with the diagram, we have this page of reading here to describe how to do it. Okay, so first ray is parallel just like before. But in this case, instead of bending towards the right-hand focal point, it's going to be bending away from the left focal point. Once you draw the refracted ray, scribble out the ray of incidence. The second ray goes towards the right focal point. And it refracts parallel. Once you draw that, scribble out the incoming ray. Now, where do these two rays cross? They don't. But if we trace them back, it appears that they came from this spot right there. So that's where the image is. It's going to be right side up. It's reduced. And the light rays are just imagined to have been back there. So it's a virtual image. Next one. Here we have the object. The object is closer to the lens. Let's think about how this is going to change things. If this object were closer to the lens, would the parallel ray change at all? And the answer is no. It's going to stay the same height above the axis because it's the same object. Parallel ray is going to hit the lens at the same spot and move up at the same angle. So the first ray is not going to change at all. The second ray, if the object is closer, it's going to be steeper to the focal point over here. And it's also going to hit the lens at a higher position. So this parallel ray is going to be higher up. So that makes the crisscross at a higher position. So it's going to be a bigger image. It will also be closer to the lens. So let's see how that works. First ray, parallel, goes away from the focal point on the left. Scribble out the incoming ray. Second ray goes towards the right focal point. And it refracts parallel. It is not a significantly higher parallel ray, but it is noticeably a little bit bigger. Okay, so where do these two rays appear to have come from? Trace the refracted rays back. Right there. A little bit bigger, a little bit farther away from the focal point, a little closer to the lens. Not a heap bunch, but some. So on this page here, we have some story problems, so to speak, about the object and focal length equation. It's the same Fedoti equation that we had with mirrors. But you have to read this section here to decide which is going to be positive and which is negative. Are they the same kind of a rule as in the mirrors? Or are they slightly different because we have two focal points, one on each side of the lens? Read it and find out.